Hey guys, how's it going? Mr. B here, and in this video we're going to be going over the chapter 3.2 notes on the International System of Units. So let's get started. In this chapter section we're primarily going to be learning about all the different units that we use in science and chemistry. These should not be brand new to you, so this should be a pretty quick section to go over. It's mostly review, okay? Alright, so first off, there are 5 SI based units. First question you might be asking is, what does SI stand for? So all the measurements that we make are dependent upon different standards, and the standards that we use in chemistry and science in general are based on the metric system. So the International System of Units, or abbreviated the SI system, is a revised version of the metric system. The 5 SI-based units that we commonly use are the meter, the kilogram, the Kelvin, the second, and the mole. Okay. Now this table here shows all the different units and their symbols and what they quantify. These are the most common ones. So length you should already be familiar with. Mass is the kilogram. We'll get into that. Temperature is Kelvin. Degrees Celsius is very commonly used in the metric system, but the Kelvin is the SI unit. We don't use Fahrenheit in science. Time is seconds. Moles is a very specific unit to chemistry, so we're going to learn a lot about moles in this course, not necessarily this chapter, but in this course, measures the amount of substance. You don't need to worry about luminous intensity or candelas because we're not going to be dealing with light and electric current. We're not going to do any electrochemistry, so you don't need to worry about amperes or amps. All right, so what metric units are commonly used to measure length, volume, mass, temperature, and energy? So the SI unit, of course, of length is the meter. It has an abbreviation of a lowercase m. Do realize it is lowercase m. There is a whole another thing in chemistry that's a capital M called molarity. Well, that'll be a very, very far thing way in the future. But either way, for now, know the little abbreviation. And then, of course, be familiar with the different metric prefixes. We use a lot of these in science. Okay, so the ones you're probably familiar with already are kilo, which means 1,000 times bigger. Centi, which means 100 times smaller, and milli, which means 1,000 times smaller, but you should be familiar with even smaller ones. So for example, micro means 1,000,000 times smaller, nano means 1,000,000,000 times smaller, pico means 1,000,000,000,000 times smaller. Especially in chemistry, the smaller metric prefixes are more commonly used than the bigger ones because we're dealing with little things like atoms. So the small metric ones are much, much more common. You need to know these, okay? Make some flashcards, do something to remind yourself, but this is something that I'm going to expect you to know. So, common metric units of length include the centimeter, the meter, and the kilometer. They give you some examples here of what each one of these would kind of be. So like a centimeter is about the width of a shirt button. Kilometer is about the length of 5 city blocks. A millimeter is about the thickness of a dime, etc., etc. So you should know which ones are bigger and smaller, but you don't need to have you don't need to know all the different reference examples. So as for volume, the SI unit of volume is not the liter, it's actually the cubic meter. The liter, which is a more common used unit and is not technically an SI unit, though it is in the metric system, is a derivation on the cubic meter. So 1 liter is the volume of a cube that's 10 centimeters by 10 centimeters by 10 centimeters. So that is 1,000 cubic centimeters, right, or 1 liter. So the liter is smaller than a cubic meter. Cubic meter is a cube that's literally a meter wide by a meter tall by a meter, thick. It's pretty big. It's a lot of volume. Okay. So do be familiar with the liter. The main thing to know here is actually this information, which we'll go over here in a second. Common units of volume include, of course, the liter, the milliliter, the cubic centimeter, and the microliter. So again, milliliters you should be familiar with. One primary thing that you really, really, really want to know, okay, and I would very much highlight this. The cubic centimeter, 1 cubic centimeter is the same thing as 1 milliliter, okay? They're the same amount of volume. So when we get further into this course and you start seeing volumes in cubic centimeters, understand that that is the same thing as milliliters, all right? It's a little bit of information that I can guarantee you will help you a lot in the future. So try to remember that. About 20 drops from an eyedropper is about a milliliter. So if you're ever dealing with a little eyedropper and you need to measure out volume, about 20 drops is 1 milliliter. A sugar cube is about 1 cubic centimeter or 1 milliliter in volume. So it's a cube that has a side of 1 centimeter by 1 centimeter tall by 1 centimeter thick. And the liter is, again, commonly used for volume. Now, granted, here in the U.S., we kind of use a mix of both liters and gallons. The gallon is much bigger than the liter, so a gallon is about twice the volume of a 2-liter bottle of soda, though it's not quite, but about, okay? So be familiar with the different units, again, for volume. So, all right, and then as for mass, the SI unit for mass is the kilogram, okay? Not the gram. Though, of course, the gram is more commonly used because a kilogram is a pretty big unit. But the kilogram is the SI unit for mass. The gram, of course, is 1/1000th of a gram, or of a kilogram. And that's the one we more commonly use, or other versions of the kilogram, such as the milligram and the microgram. Okay? Again, know what these prefixes mean. Know what kilo means, know what micro means, know what milli means. All right. Now, other than mass, weight is something that is commonly comes up quite often in science. But understand what weight means and what mass means. So, weight, even though the words weight and mass are oftentimes kind of used interchangeably, they do mean different things. Weight is a measure of force. So, when you're taking your weight, you're actually measuring the force of gravity that is pulling you down to the floor. Whereas mass is a measure of how much stuff is in your body, okay? It is possible to be weightless, but it is not possible to be massless unless you don't exist. So if you go into outer space, you will have no weight because there's no gravity pulling on you from Earth. However, you still have mass because there's still matter that makes up your body. So even though these two words are used interchangeably, and even I use them interchangeably on a regular day basis, they do not mean the same thing. You should know the difference between the two. All right, and then unit of temperature we have is the Kelvin. Now, temperature is a measure of how hot or cold an object is. It's kind of layman's terms. It actually means a little bit more than that, but we're not going to get in that much in depth. We use thermometers, of course, to measure temperature. There are two units of temperature that we commonly use in science. It is the degree Celsius and it is the Kelvin. The Kelvin is the SI unit, but the degree Celsius is probably more commonly used, to be honest. So on the Celsius scale is based on the boiling point and freezing point of water. So water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. And the Kelvin scale is also based on the freezing boiling point of water, but it's also based on what is known as absolute zero. So at 0 degree Kelvin, or 0 Kelvin, there's no degrees in Kelvin, but at 0 Kelvin, that is at the theoretical temperature where all motion comes to a stop. Okay. Now, when you cool things down, all the particles that are inside of objects on a daily basis are constantly vibrating. Okay. When you lower the temperature of something, those particles start to move slower and slower until theoretically you could get the temperature low enough that they don't move at all anymore and they completely stop moving. That is what we call absolute zero. Okay. It's theoretical temperature. We've never actually reached it before, though we've gotten very close. And so the Kelvin scale is based on this idea or concept of absolute zero. Now, to go between the two scales, it's actually really simple. The Kelvin scale is just 273 higher than the Celsius scale. So if water freezes at 0 degrees Celsius, it would freeze at 273 Kelvin. Okay, so you're just taking 0 and adding 273 to get to Kelvin. If water boils at 100 degrees Celsius, then in the Kelvin scale, it would boil at 373. Okay, absolute zero Kelvin would be negative 273 Celsius. So it's easy to go back and forth between the two. Again, you might think it's silly, like why are we adding or subtracting 273? That seems silly. Why don't we just use Celsius? Scientists just really like the idea of a zero, absolute zero. They just like that concept. So anyway, don't worry too much about it. So this just shows a picture between how to convert between Celsius and Kelvin. Again, you add 273 or minus 273, very simple. So all right, we're not going to go through that sample problem, but keep on moving. All right, and the last little bit here talks about units of energy. I'm going to go over this, but you don't need to worry too much about this. We're not going to deal with energy or joules or calories in chemistry because we don't do any thermochemistry. So energy is the capacity to do work or to produce heat. The joule and the calorie are the common units of energy. And this calorie here, this unit of calorie, that is calories of heat, okay? Thermal calories, not nutritional calories. So nutritional calories, of course, is how much energy your food has, right? When you eat food, you wonder how many calories it has. That's the nutritional calorie. This calorie here we're talking about is a thermal calorie, which is how much energy, heat energy, is required or is input into something. So they're based on the same concept. They're both energy, but they're different. So don't get calories and nutritional calories confused. So the joule is the SI unit of energy. It has a capital J. If you had me last year in 9th grade general science, you would know that the joule is the unit of work. So work and energy, we measure in joules. The calorie is, again, a unit of energy, and it's the quantity of heat that is needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. To convert between the two, 1 calorie is roughly about 4 joules. So, you can convert between the two if you need to, pretty simply. This picture here shows a house with solar panels, and the solar panels basically take energy from the sun or radiant energy from the sun, convert it into electrical energy, which would be in joules, and then that is used to then heat water and power appliances and stuff like that. So, all right, so that is all of the different units that we deal with in science. Again, should be review, shouldn't be a whole lot of brand new information. If you want to see me go over the practice problems, there's a video of me going over that, so you can watch that separate. This was just about the information. So, all right, guys, that's it for chapter 3.2. I'm Mr. B. If you have any other questions, again, always feel free to email me, talk to me in person in class, or we could always do a Google Meet. All right, I'll see you in the next one. Bye.